Hi guys. Okay, so here we are for more properties of polynomials, part 2. We're going to look at zeros of polynomial functions as well as some end behavior. Okay, now for each of the functions graphed below, we're going to state the end behavior and the zeros of their functions. So we have here the graphs of 3 different functions, f of x, g of x, and h of x. Now it turns out that f of x is a cubic function. Okay, so it's a cubic function. Now let's find the left end behavior. So the left is as we go off the graph to the left, our x values are getting smaller and smaller and headed to negative infinity. What happens to our function values? Our function values as we go off to the left, they are falling, which means they are also getting smaller and smaller without bounds. Okay. Let's take a look at our right end behavior. The right end behavior is as we go off the graph to the left, as the x's increase without bounds, so the x's we say head to positive infinity. What happens to our function values? Well, our function seems to be rising as we move to the right, so we say that f of x is headed to positive infinity. Now, positive infinity is not a number, remember. That just means that our function is rising without bound. Now, zeros, those would be the x-intercepts. So we need to look for our x-intercepts or our zeros. I see one here at -2, one at -1, and one at 1. So -2, -1, and 1 are our zeros. And notice this was a cubic, which is a third degree polynomial, and we found 3 x-intercepts or 3 zeros. Wonderful. Okay, let's take a look at g of x. Now, g of x is a quartic function. I know this because I typed the function into the calculator, so I know what I graphed. All right, let's take a look at the left end behavior. As we go off to the left and our x's get smaller without bound, what happens to the function values of g of x? Well, if I look as I go off to the left, the graph is rising without bound. Good. Now let's take a look at the right end behavior. As we go off to the right, as our x's get large without bound, they head to positive infinity. What happens to our function values? As we go off to the right, this function is also increasing without bound, so we say headed to positive infinity. Now we want to find the zeros, so we're going to look for x-intercepts. Well, that looks somewhere about halfway between -2 and -3, and it is in fact -2.5. And then it looks like there's another root here at 2. Now I want you to keep this in mind. We had a quartic, which is a 4th degree polynomial, but we only found 2 roots, or 2 zeros. We're supposed to have 4. We're going to come back to that in a minute. Okay, just keep that in mind there. Now let's take a look at the graph of h of x. H of x is a quintic function. So remember, a quintic function is a 5th degree polynomial. So now this 5th degree polynomial, we're going to look at the left end behavior. So the left, as we go off to the left, the x's are getting smaller without bound. What's happening to our function values? As we go off to the left, the graph is falling, so we say h of x values are also headed to negative infinity. Now the right end behavior. As we go off the graph to the right, that's as the x's get large without bound. They head to positive infinity. What happens to those function values? As we go off to the right, our function is increasing without bound. Those values are getting larger and larger. Okay, now the zeros. So the zeros, where do we cross the x-axis? At -4, at -2, here at 2, and again at 5. Now again, here's something to think about. We have a quintic, which is a 5th degree polynomial, which should have 5 roots. We only found 4 zeros. Something to think about. Okay, so we need to define a new term. We're going to define the multiplicity of a zero. The multiplicity of a zero is the number of times a zero is a root. Now, when you factor, the factor may appear more than once. For instance, if you factor and you get x minus 1 times x minus 1 equals 0, you're going to get the root x equals 1 twice. That means x equals 1 is a root of multiplicity 2. Now the graph is only going to touch the x-axis at x equals 1 once, but it's a root twice because it comes from two different factors. And that's what happens when we have a root of multiplicity greater than 1. So we're going to take a look at these three graphs again, okay? So now, this is the graph of f of x, okay? The first one, I just brought it down here so I could see. In the graph of f of x, all the zeros have a multiplicity of 1. Notice, every time the graph cuts through the x-axis, and the graph doesn't have any major changes to what's going on. Okay, it cuts through the x-axis, there's no major changes to what's going on. Now, let's take a look at g of x. Now, g of x, the root at negative 2.5, has a root of multiplicity 1. The graph is cutting through the x-axis, and there's really no major change to the graph. However, at x equals 2, this is a root of multiplicity 3. I know that when I factor it, I'm going to get that particular factor 3 times so that I get the root x equals 2 3 times. Now look at the graph. The graph passes through the x-axis, but do you see how it's curved down before we get to the x-axis? And then it's curved up. We say that it's concave down when it's curved down, and then it's concave up when it's curved up. So when the graph cuts through the x-axis but changes concavity, the way the graph curves, the curvature of the graph, that's when we have a root of multiplicity 3. Now let's take a look at the third graph. This was the graph of h of x. Now, h of x has zeros at x equals negative 4, x equals negative 2, and x equals 5 that each have a root of multiplicity 1. Notice the graph cuts through at each of those 3 points and no major changes to the graph. The curvature doesn't change. It's curved down, it's curved down, it's curved up, and it didn't change. However, if you look at x equals 2, and I tell you that this is a root of multiplicity 2, notice at 2, the graph is tangent to the x-axis. It comes up, it touches the x-axis, and then bounces off it. It does not cut through the x-axis at all, and that's important. So let's summarize what we just said, okay? And one of the other things we need to remember is that the sum of the multiplicity, so it doesn't have to be the number of x-intercepts, but the sum of the multiplicities of the zero and the degree of the function are equal. So you don't have to have, if you have a fourth degree polynomial, you don't have to have 4 x-intercepts, but the multiplicities of the roots will give you the same degree. For instance, if we go back here, remember, this was a third degree polynomial. 1, 2, 3 adds to 3. This one was a fourth degree polynomial. This was a root of multiplicity 3. This was a root of multiplicity 1. 1 plus 3, that gives us 4. h of x was a quintic, a fifth degree polynomial. This was a root of multiplicity 2. plus 1 plus 1 plus 1. So 2, 3, 4, 5. When you add up the multiplicities, that will be the same as the degree of the function. Okay? Now, let's describe the behavior of the graph as it approaches a 0 whose multiplicity is 1. If the multiplicity is 1, the graph crosses through the x-axis without changing concavity. And remember, the concavity is the curvature of the graph. It's the way that the graph is curved. Okay? Now let's describe the behavior of the graph as it approaches a 0 whose multiplicity is 2. If the multiplicity is 2, the graph is tangent to the x-axis. Okay? And finally, if the multiplicity is 3, the graph crosses through the x-axis and changes concavity. And we will look at this more in class. I do promise that, okay? We will look at this and we're going to examine this a lot. But looking at the graph now, it's going to be easier to tell how many roots there are, what degree the polynomial is, which root happens more than once. So here are some examples. The first example, we have f of x is x cubed plus 2x squared minus x minus 2, and they've given us the graph. Now notice the highest power of x is 3. That makes this a cubic function. A third degree is called a cubic. Now, they want us to find the roots, tell the multiplicity of the root, and how we know what the multiplicity is based on the behavior of the graph. So I'm going to start working from left to right. Okay, so the first root that I see is that x equals negative 2. And I believe that root is a root of multiplicity 1 because the graph crosses the x-axis without changing concavity. Okay, and the concavity is the way that the graph curves. Remember that. Okay, it's coming through the graph, the x-axis here, and it's not changing the way it's curved. The graph is slightly curved down the whole time. Now let's take a look. The next root I see is at negative 1, and it doesn't matter what order you're finding these roots in. I'm just working left to right. And I would say that again, this is a root of multiplicity 1 because the graph also crosses the x-axis. And I'm going to abbreviate without. W/O means without changing concavity. And we're going to do one more. The next root is at positive 1. And again, the curvature of the graph or the concavity is not changing. So it's a root of multiplicity 1 because the graph crosses the x-axis without changing concavity. Now, if you look at our multiplicities, 1 plus 1 plus 1 adds up to 3, and that is the degree of our polynomial, so we know we have all of our roots. Let's try another one. h of x is 2x cubed minus x squared minus 4x plus 3. And again, this is a third degree polynomial, which makes it a cubic function. It also means we're going to have 3 roots. I'm going to find my first root. It's about halfway between negative 1 and negative 2. So that's going to be a root of negative 1.5. Now when I look at the graph, it's crossing through the x-axis and the curving isn't changing. So that's a root of multiplicity 1 because it crosses the x-axis without changing concavity. Now I see another x-intercept at 1. However, this time the graph is tangent to the x-axis. That means this is a root of multiplicity 2. Now if I add my multiplicities, 1 plus 2, I get 3, and that was the degree of my polynomial. I have all my roots. Good. Last example for today. P of x is 2x to the fourth minus 7x cubed minus 6x squared plus 44x minus 40. And we have a 2x to the fourth as our leading term. The highest power of x is 4, which makes this a quartic function and means we're going to have 4 roots. So I'm going to start, and the first x-intercept I see is here, about halfway between -2 and -3. So at -2.5, I've got a root. And if I look at the behavior of the graph, it's cutting through the x-axis. So it crosses the x-axis, but the curvature or the concavity is not changing. And we'll talk more about this concavity in class, so not to worry. So that means that the multiplicity is 1. Now, let's see. I see another root right here at 2. Now this time, it's still true that my graph crosses the x-axis. But notice the graph is curved down first, and then on the other side, it's curved up. So it went from curved down to curved up. So this is concave down and this is concave up. So it crosses the x-axis and changes concavity, which means we have a root of multiplicity 3. Now if we look at our multiplicities, 1 plus 3 is 4. We have 4 roots for a 4th degree polynomial. We are good. All right, so we're going to stop here. We learned a lot today. We were looking at polynomial functions. We're looking at left-end behavior, right-end behavior. We're looking at all the roots and the zeros, and we're determining how many times those roots occur by looking at the graph. Is it a root of multiplicity 1, a root of multiplicity 2, or a root of multiplicity 3? All right, guys, have a great day. I'll see everyone soon. Bye.